The creation of our optimal truss bridge design for our first project of Engineering 101 has collected the final results given in this presentation. These results and bridge designs were created by Nathan Hunstad, Samuel Risser, Sean Schultz, and Madison Yost.
Through design and testing, the Warren, Pratt, K-Truss, Fink, Parker, Waddle A, Pennsylvania, and bowstring trusses were found. Through testing these, we found that the Parker truss was the best design to continue to develop further and eventually produced as our final result. The final cost of the Parker truss was $248,551.46. All the members of the bridge within the tension and compression strength range of 0.2 to 0.4. Our objective was to build the most cost-effective, aesthetically pleasing, and safest bridge design possible using the West Point Bridge Designer software, basing off of the 8 truss designs we were given. The starting conditions for the 32-meter bridge span were a deck elevation of 12 meters, standard abutments, no pier, 1 cable anchorage, high-strength concrete, 0.15 meters thick, standard 225 kilonewton truck that was 2 lanes.
Throughout history, trusses have been made from a variety of materials and used for a variety of purposes. The first documented version of a truss bridge was in the 16th century by Andrea Palladio. Truss bridges increased in popularity in the United States in the 1700s and the 1800s. Most of the designs made during this time were for railways, which led to the creation of many different varieties. Some popular designs were the Pratt, Warren, Parker, Camelback, and Pennsylvania trusses.
While performing a structural analysis, the main forces being used are tension and compression. Tension is when you try to pull something apart, while compression is the opposite when you try to push something together. In order to determine the forces of each member of the bridge, you need to use a vector. You find these vectors by taking the angle and using sine, cosine, and tangent. When you find your force on a member, you can figure out if the member will hold or fail if you know the tension and compression strength of the material you're using.
Abutments are on the walls of the edges of the bridge, and they hold the vertical and horizontal pressure of the bridge. A pier is in the middle of the bridge and is mainly for supporting the vertical pressure. The main factors that go into the designing a bridge abutment are cost, durability, strength against erosion, and lengths to the ground. The 5 main abutment designs are full retaining, semi-retaining, sill, spill through, or open, and pile encase. All of these have varying levels of those main factors.
Trusses are not only used for bridges, they're also used a lot in architecture, specifically being used in roof design. A lot of these designs are very reminiscent of the Pratt truss in a bridge, but it allows the roofs to have more structure and be more stable. Steel beams and skyscrapers also use trusses to help keep the beam stable when going against high winds in order to keep the building stable instead of falling down, because the trusses allow for the I-beams to have more stability. They can also be used for interior design through the exposed beams that you see in modern houses and in the windows that you see in old churches.
For our methodology, 2 varieties of truss were assigned to each group member. These trusses were then researched to find the proper design and modeled in West Point Bridge Designer 2020. The models were inspected to determine which had the lowest cost and the highest safety score, and then the chosen model was revised to optimize the performance.
2 trusses had significantly higher overall scores in our results that we have discovered. These trusses were the Waddle A truss and the Parker truss. The Waddle A truss had the highest safety score, as many of the members had rather low force to strength ratios within the parameters. However, the cost is relatively high, reducing its overall score, whereas the Parker truss had members at and near the borderline of the parameters of the force to strength ratio, which reduced its safety score, but it had the lowest cost of all the bridges as well as the highest aesthetic score. This made the Parker Truss the ideal design and made us decide to go with it for further evaluation and edits.
Here you can see the final design and member data for the chosen bridge. All of the members fall within the given force to strength ratio range, and no members on the bridge cause it to fail.
After reviewing all of the cost and safety scores of the other bridges, it was determined that the Parker Truss had the most optimal design and the lowest cost at $248,000, $511 and 46 cents. Since the bridge software only is two-dimensional, there were other things to account for further development. You would have to, if you're going to build this in reality, you would have to find a way to connect the two trusses together to support them. You would also have to design gussets and other ways to join the beams together. In the software, we just placed a member, where in reality is much more complicated than that. If we were to build the bridge, we'd also have to make a construction plan for how and in what order it would be built.